Welcome to episode 5 of this series on variance of a random variable. So far, we have covered what is variance, how we can calculate variance, what are the different unbiased and biased estimators for calculating variance, and how we can correct the biased estimator using the using Bessel's correction. So we have looked into like how variance can be considered as some notion of spread or dispersion around the mean for a probability distribution. So, is variance the only way of measuring spread in a probability distribution? And there comes entropy. So, in this video, we'll try to look into some subtle differences between variance and entropy, where both of them capture some notion of spread for a probability distribution. So, let's start into this. So, variance measures the numeric spread around the mean. And on the other hand, entropy measures the information content in the distribution. So what it means is entropy tells how surprising or how unpredictable the outcomes are. So if the information is high, we would be more surprised with the outcomes, or we would be considering the outcomes as more unpredictable. So it's mostly related to the spread of values versus the unpredictability of the outcomes. How can we, let's say, mathematically define that now? So entropy, based on the formula, is given by the expectation of the information content in a distribution. This information content is nothing but negative log likelihood of the samples. So it's given as basically the average information that is there in the distribution. On the other hand, variance is the expected square deviation of the samples from the mean. Now, if we have a closer look, we can observe that we only need the samples as their likelihood. So we don't always have to deal with the numerical value of the sample. So we only need the probability for the samples, and that is enough for us to calculate the entropy. On the other hand, if we see for the variance, we actually need the numerical values in order to calculate the mean and in order to calculate the deviation so that we can get the variance. So this is the very first difference based on the mathematical formula, like how we do necessarily require the numerical values for the sample as compared to when we're calculating entropy, where we just are dealing with the probability values. Now, if we see here, entropy only needs probabilities. You can calculate probability and for that reason, we can also calculate for entropy for categorical data, but we might not be able to calculate variance for categorical data. So let's say, for example, if we have a distribution looking like this, and these are real numbers, let's say house prices, we can calculate the mean, we can calculate the dispersion or the spread so that we can calculate the variance in this case. And we can also, by the way, calculate the entropy in this case. On the other hand, if we have, let's say, a distribution of colored balls, and we have the probability or looking something like this, or like the number of balls in a bag like this, we can calculate the entropy, but there is no mean by which we can calculate the variance here, because we're not dealing with numerical values. Same is the case with the distribution of, let's say, animals, cat, dog, and bird in a zoo. And again, we can calculate the entropy, but we might not be able to calculate the variance in this case. So we can also say that the high variance can often correlate with higher entropy, and it totally depends upon the shape of the distribution, and we'll get to that later. But in this case, let's say, for example, we can see that this distribution can have a higher entropy, a higher variance as compared to a distribution that can probably look something like this. So this distribution, the brown one, is having lesser variance and as well as less entropy as compared to this one. So it can happen that high variance correlates with high entropy, but it totally depends upon the shape of the distribution as well. Also, we can find that scale matters for variance and not for entropy. Given an example, let's say we have a data set of numbers 10, 20, and 30, where the variance comes out to be, let's say, 67. So let's say we have this distribution, and we can assume that these numbers are like equally likely. Similarly, if we have a data set B, and we are doing nothing but multiplying this by 100, so we have this one. And now the variance, if you see, has exploded. But if we calculate the entropy for both these data sets, or the data distribution, if we have a distribution for the data set A, something like this, and for data set B to be something like this, we can see that the spread of values in both these cases is actually controlling the variance. So this would be exploded, but because all the values are equally likely, the entropy is going to be same for both these distributions. So dataset B has massive variance, but identical entropy if the values are equally likely. So in this case, the unpredictability or the information content in the distribution is the same. So it's invariant of the scale, or basically the if you multiply these numerical values with anything, the entropy is still going to be the same, but the variance might explode. Now, in this case, we considered an example where the entropy is same, but the variance was different. Let's take another example where, let's say, for two distributions with the same variance, let's see how it can affect the entropy. So let's say, for example, we have a uniform distribution that is like from 0 to 100. This is the distribution. So the mean would be somewhere around 50, and it is having high variance and high entropy. And this would become unpredictable, like highly unpredictable, because this is a uniform distribution. And similarly, if we have another distribution that is the normal distribution, that is again the mean is somewhere around 50, but it's tight around 50. Basically, it's having a low variance, and then we can consider that as discussed in the previous example, that we can have low variance and as well as low entropy, and we can see it from the shape of the distribution that it could be like a little bit predictable as compared to this one. Similarly, if we have another distribution that is a bimodal distribution, so let's say we have a bunch of zeros and a bunch of hundreds, and that's it. So we are kind of distributing the values here and distributing the values somewhere here. So now in this case, we see that there are like, this is an example of high variance, but because we only can see that there are only two possible outputs, either 0 or 100. So it could be a little bit predictable if we, let's say, if we have some more values in between that are very small in probability. But so it is highly becoming predictable. So entropy captures the pure how hard it is to predict a concept independent of the scale or independent of whether the data is numerical or not. Variance is more about calculating the numerical dispersion, and where like entropy is again about the information surprise, or basically how hard or easy it is to predict a particular value. Let's take some real distributions again, an example. So let's say if we have a Gaussian, a Laplace, and a uniform distribution with having the same mean as 0 and variance 1, we can observe that from this plot that this Gaussian distribution is smooth and is most spread out. That's why it can be considered as high entropy. Laplace, on the other hand, that is uh, this one. Sorry, I think so. I have messed up the colors, but yeah, it's fine. So this is the Laplace. Blue one is the Laplace, and we can see that it's also a little bit spread out, and it is having some medium entropy. And on the other hand, the uniform distribution, that is this green plot, is flat. Like the values are equally likely here, but if you see that it's truncated here, so it's bounded by some values, negative, I suppose, yeah, somewhere here, and that's why it is having the lowest entropy of like approximately 1.242. So, but isn't the case that we discussed, and we probably know that a uniform distribution is supposed to be having a higher entropy as compared to other distributions, because it's like all the values are like equally likely. How is in this case that the uniform distribution is having a lower entropy than the other two distributions? And the answer lies in the fact that it totally depends upon whether we are considering a bounded interval or not. So let's say if the values of x are in the range of a to b, and the uniform distribution a to b in that case would be having the highest entropy, and no other distribution in this interval would be more uncertain, because I mean it's like all the values are equally likely, and that's why uniform distribution would have the highest entropy if the interval is bounded, or the values of x are, let's say, in between a to b, and the uniform distribution is also bounded in this interval. But on the other hand, if we have a fixed mean and variance but unbounded support, or basically unbounded interval, then the Gaussian or normal distribution has the maximum entropy, because we observe that the tails can just keep on extending infinitely, and the uniform distribution can be just simply truncated after a particular interval, where the Gaussian can just keep on spreading its tail. So the uniform distribution can have the same mean and variance as the Gaussian. That's what we saw in the plots. But the finite support cuts off the uncertainty. So some sort of uncertainty or unpredictability is cut because of the finite support. And let's say, for example, if we have a uniform distribution looking like this, they are still having the same mean and mean, like mean 0 and variance 1. Same thing goes for this one. The entropy would be looking something like this for uniform, and entropy for Gaussian would be something like this. And we can see that it's for Gaussian, it's a little more than the entropy of uniform distribution. So the statement that says that isn't the uniform distribution always have the maximum entropy is only true when the support is fixed and bounded. But I mean, as we saw in the example, that we actually had a fixed mean and variance, but it was unbounded. So that's why Gaussian had the maximum entropy. So now let's take this example. Now, if we have discussed a good amount of stuff uh, in terms of the differences between entropy and variance, what do you think is this case? Is this the case of variance, or is this the case of entropy, or like what does this diagram explain better? So in this we can see that this can explain variance a lot better in terms of it is actually considering the stretch of the values or the spread of the values that we can see. And in this case, it's still the variance, but we can find that it's also about the spread of the mass. And when with mass, what we mean is mass basically is equivalent to belief. So, how much belief do we have in the values that we are considering, and how much belief or mass are we putting onto those values defines entropy. So, if we let's say if we have a distribution looking something like mm, this, so this probably would mean that it can have the stretch of values are considerable, but because the likelihood of these values is small, so it might happen that the variance is also small. And because we are also putting major chunk of the mass at these values, so in this case the variance and as well as entropy might be lesser, uh, if we consider this kind of shape. Now if we consider another shape, as in something like this. Now in this case, we are still trying to put good amount of mass only at like two specific values, but we can see that the likelihood of outliers, the mean would be somewhere here, so the stretch around mean is still considerable. So in this case the variance might be huge because the spread of values is huge and the likelihood of outliers is also high. So it means that it might explode. There are chances of variance to be higher, but again the entropy might still be lesser because we are trying to put most of the mass at like very specific values and not anywhere uh, in this interval. So again, so this is in this example, variance could be high, but the entropy can still be low. So we see that it totally depends upon the shape of the distribution and how we are distributing the mass, or how we are actually spreading the values in order to calculate variance or entropy. So variance is the spread of values, whereas entropy is the spread of mass or beliefs, uh, 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 considering the possible samples that we have. So that brings us to the end of the series. So far what we have covered is why variance matters. First of all, like variance matters because we care about the risk, and we can see from this diagram as well, like there is a huge like good amount of risk involved in terms of the outliers, because the outliers are having like high likelihood. So variance corresponds to the risk that could be there, and the predictability of numerical values being picked or sampled. We also looked into different statistical moments like mean, that basically tells us the location of the distribution, variance as the spread of the values, skewness as the asymmetry in the distribution, and kurtosis corresponds to how heavy the tails are. And all these moments can be considered to give good amount of information about the distribution. We also looked into how we can calculate variance and how does it depends upon from where the data is coming from, whether it is coming from population or whether it is coming from a subset of a population. Then we considered, like, given a subset or a sample, how we can estimate or what are estimate the variance uh, of the population, where like estimators are just simply rules or statistical functions that can be used to estimate the true parameters from whatever available data that we have, or basically the sample data that we have. After that, we looked into the actual formula based on how we can calculate the variance based on just the sample data, where the population variance, that is the true spread is given by this formula, and where the sample variance, if calculated based on the deviation from sample mean and dividing it by n, could be a biased estimator and can be an underestimate or underestimates the true population variance, where if we divide it by n minus 1, it could be an unbiased estimator, and that extra bias that we have is nothing but the variance in the sample mean, and that is this missing spread that we have. And finally we covered that the difference between variance and entropy, where variance measures the numerical spread around the mean. It's kind of a measure of a distance, where entropy information tells us about the information of the surprise content in the distribution. It's actually a measure of distribution or measure of unpredictability. It tells us how we can distribute the mass or beliefs amongst the different samples. So it's mostly about the spread of mass, and variance is about the spread of values. I hope that you like this series. And yeah, till we'll meet you in some next videos. Till then, happy learning. Thanks.